Okay, let's talk about the photochemical reactions of the Sydnone molecules, or let's say the 1,2,3-oxadisolium 5 olates. You can see here this is the very first reaction in which the main reactant is what? It is our Sydnone mesoionic, which can actually act as a 1,3 dipole, and upon a reaction with the symmetrical type of alkyne, something like this, under photochemical conditions, I mean HNu, it results in the generation of this type of product molecule, which is basically a type of a pyrazole, right? Because in this 5-membered structure here, the 2 nitrogen atoms are present adjacent to each other. Such kind of heterocyclic molecules are known as the pyrazoles, right? And now if you remember the very last lecture of the Sydnone mesoionic molecules, there was a reaction in that video which was with the symmetrical type of alkynes undergoing a regular type of 1,3 dipolar cycloaddition, giving a similar type of pyrazole molecules, right? And now if you go for the comparison of this pyrazole here, which we have got in our last video lecture, by a regular type of dipolar cycloaddition with this pyrazole here, which we are getting now because of the photochemical reaction, you will see that both these pyrazoles, I mean this one here as well as the pyrazole which we are getting because of the photochemical reaction, I mean this one here, they are isomeric in nature, because you can see here in this case the R1 as well as the R2, they are present on the adjacent atoms here, right? On the other hand, in this reaction, I mean the photochemical reaction, the R1 here and the R2 group here, they are present on non-adjacent atoms, right? So these are what? These are isomeric type of pyrazoles. But one thing is for sure, that the Sydnone mesoionic molecule, upon reaction with a symmetrical type of alkyne, whether photochemical or a regular type of cycloaddition, it always gives a molecule of pyrazole, right? And now it's time to look into the mechanism of this photochemical reaction. So it goes like this actually, in which you can see here that the mesoionic molecule structure of this kind can always be represented in an equivalent type of structure, in which according to this symmetrical axis, if we go for the drawing of 2 double bonds, the first one on this side and the second one on this side, with a positive charge here on this heterocyclic atom, and then a negative charge as usual here present on this exocyclic atom, this will be what? This will be an equivalent, let me write here, this will be an equivalent structure for the main mesoionic structure, I mean this one here, right? And also we can always go for drawing the resonating structure for this type of equivalent structure. And how we can do that? Simply by shifting these electrons of the negative charge in between this carbon and oxygen bond, and then these electrons obviously will shift here to this carbon atom bearing this R2 group here, and of course a negative charge will now appear, right? And moreover, this time let us say we are also going for this type of resonance in which these pi electrons are shifting onto the nitrogen, such that they can be shown in this way. But because of this, what will happen is a positive charge will now appear on this nitrogen atom, I mean this one here, right? So basically you can see here that it is actually our main 1,3 dipole type of structure corresponding to the main Sydnone mesoionic molecule, right? And because it is a type of a photochemical reaction, so such type of HNu will be very common on these reaction arrows here, right? So basically this HNu is what? It is the energy which will be provided in the form of photons to our molecule, such that those reactions which otherwise are not possible, they will occur quite easily, right? For example, in this case, you can see here that this nitrogen here is having this positive charge, and this carbon atom here is having a negative charge. So although the opposite charges attract each other and may result in the formation of a bond, but because in this case the bond formation will be of what type, it will be leading to the formation of a three-membered cyclic structure here, which we all know is quite unstable, right? But not to worry, we are providing energy. Yes, we are providing energy in the form of H nu here, such that the things which seems impossible, they can also happen here because of this much amount of energy, right? So it will be leading to the formation of a bond in between this nitrogen and this carbon atom having a negative charge, resulting in the formation of an intermediate something like this. Okay, and after that what is going to happen is that these electrons will shift here, sending these electrons onto this carbon nitrogen bond, giving of course a double bond here in this way, and releasing a molecule of carbon dioxide from this reaction. We will end up with this type of intermediate here, right, in which a three-membered cyclic structure is present with two nitrogen atoms and one double bond, right? And after that, two different pathways are now possible. The first pathway is what? Let me draw the same structure twice here. I mean this structure, so that I can show you the first pathway, which goes like this here. I mean these electrons shifting here and then these electrons shifting here on the carbon atom. And it will be better if instead of this single-headed arrow we are showing a double-headed arrow here, because it is nothing, it is the resonating structure for this intermediate here, right? And you can see here that in this resonating structure now, because these electrons are going from here to here, obviously it will give a double bond in this way with a positive charge here, because nitrogen is forming 4 bonds here, right? And moreover, because these pi electrons are shifting to this carbon atom bearing the R2 group here, so obviously it will now be having a negative charge because of the movement of these electrons onto this carbon atom, resulting in the formation of this type of resonating structure. And we are talking about what? The very first pathway, right? And now let's have a look at what is going to happen in case of the second pathway, in that the electrons or the resonance, I mean the second resonating structure, it can be shown in this way. I mean these electrons shifting from here to here, and this bond here, I mean bonded electrons going to this carbon atom, resulting in the formation of first of all a double bond here. I mean this double bond because of the shifting of these electrons in between these two nitrogen atoms. Obviously now, because it is forming 4 bonds, so a positive charge is a must here. And then the cleavage of this bond will take place from here, because the electrons of this bond, they are now coming to the carbon atom here, you can see here. So it will now be having a negative charge like this, okay? And once again, this second pathway is what? It is some sort of a resonating structure here, some sort of resonance. So better to show a double-headed arrow even in this case here in this way, right? So this is the resonating structure of this type of structure. And moreover, another resonance here can be shown, and it will be like what? It will be shifting of these electrons from here to here, giving a triple bond, something like this. And then shifting of these electrons of the pi bond onto the nitrogen atom, such that this will now become a single bond in this way. And of course, a negative charge will now appear on the nitrogen atom, right? So now finally, if we try to compare this resonating structure, I mean this one here, with this resonating structure, which are actually the products of two different pathways. From this first pathway, we are getting this structure. From the second pathway, we are getting this structure here, right? And we can say here that as compared to this structure, this resonating structure is quite useful, because it is appearing in the form of a 1,3 dipole, right? This portion of this resonating structure is actually a form of a 1,3 dipole, which can give rise to different type of 1,3 dipolar cycloaddition reactions, That is why I have written here a significant structure, and it is quite useful, right? On the other hand, if you give a look on this type of resonating structure, first of all, the nitrogen here is having a positive charge, means unstable. The carbon here is having a negative charge, means unstable. Moreover, it still contains a three-membered unstable ring structure. On the other hand, this structure here is simply opened up, and now there is a possibility of different kinds of reactions from this type of resonating structure, right? So this is what this is like a dead end for our reaction. This is like a dead end for our reaction. No further reaction from this pathway. So now let's go and check what will happen in case of the second pathway. I mean along this direction here, right? So when we will be moving along this direction, we have got this resonating structure which can be redrawn in this way here, right? You can see here, this is the R2, single bond, carbon here, then is the triple bond, nitrogen having a positive charge, a single bond, nitrogen having a negative charge, and then is our R1 here, right? So it will be acting as our 1,3 dipole type of molecule, and we are adding, because here this type of dipolarophile, which is a symmetrical type of alkyne. So as usual, the negative end of the dipole will be interacting with this carbon atom because it is symmetrical. There are no issues of regioselectivity. Both the carbon atoms are same here. So the negative end can interact with any of these carbon atoms. Let us say it is interacting with this one here, and then the second carbon atom will be interacting with the positive end of the dipole in this way, right? Such that now we will end up with what? We will end up with E here, E group, single bond. This will now become a double bond carbon here with the second E group, and now a single bond formation will take place in between this carbon and this carbon atom here. Let me show here in this way, having R2. This will now become a double bond nitrogen, a single bond nitrogen, on which initially the negative charge was present, but now a bond formation will be there in between this nitrogen and this carbon atom. So let me show here the bond formation in between this nitrogen and this carbon here, and it is also having what? It is also having the R1 group here, right? So you can see here, you can compare here that this structure here is exactly equivalent to this structure, which is what? Which is a type of a pyrazole molecule, and this is the sole product of this photochemical reaction, which is in between the Sydnone molecule, Sydnone mesoionic molecule, and this type of symmetrical alkyne, resulting in the formation of pyrazole under photochemical type of reaction conditions, right? So this was the very first reaction, and now let us have a look on the second reaction, which is about what? Which is about the photolysis of Sydnone, but this time in the absence of any type of external dipolarophile, right? So in this reaction, you can see here, this is the main reactant molecule. Let me write here, this is the main reactant molecule, and because we are talking about the photochemical reactions, you can see here we are providing energy in the form of H nu, and instead of this Sydnone mesoionic, you cannot see any other reactant molecule here, means this reaction is completely occurring in the absence of an external dipolarophile. We are not adding any kind of dipolarophile here in this reaction, right? So whatever will be there, it will be in between this reactant molecule. So you can see here the result is what? That this type of photolysis reaction results in the formation of a molecule of triazole, because it contains 3 nitrogen atoms. Moreover, it is a 5-membered ring here. So triazole molecule, and secondly a structure something like this, which is known as the oxadiazole 2-one, right? So the photolysis of Sydnone in the absence of any external dipolarophile results in the formation of triazole and a molecule of oxadiazole 2-one here, right? So now it's time to go into the mechanistic details of this reaction. So once again, I can say here that we can always draw an equivalent structure for this type of structure of our mesoionic, and that will be like this here, right? So let me draw here 3 lines, means which are the sign of equivalence. So this structure here is exactly equal to this type of structure for our Sydnone molecule, and it is representing what? It is representing a 1,3 type of dipole here, right? So once again, because we are providing here lot amount of energy in the form of H nu, so those type of reactions which otherwise seems impossible or which otherwise seems non existing, they will just set up here, resulting in the formation of a bond in between this nitrogen having a positive charge and this carbon atom over here having a negative charge, right? So you can see here the formation of a bond in between these two atoms, resulting although in the formation of some unstable type of 3-membered ring structure here, right? And as usual, it will be releasing a molecule of CO2 in this way, giving what? Giving CO2 out of this system, and moreover a double bond in between this carbon and this nitrogen atom here, which you can see here, right? This carbon and this nitrogen here will now be having a double bond, as we have just seen in the last reaction, right? And after that, once again in this case, like this reaction here, 2 different pathways will be possible. The first one will be this, the second one will be this here. So following the second pathway, I mean this pathway in which the resonance is being shown in this way, cleaving this carbon nitrogen bond from here, giving a negative charge, moreover a double bond in between this nitrogen and this nitrogen. So we will be using this type of resonating structure here, because it will be going towards something more viable, towards something more stable type of product molecule, right? So once again, it will be better if we show here a double-headed arrow in this way, because it is just a resonating type of structure, right? And also we can go for the second resonating structure in the same way, means this negative charge is shifting in between the carbon and the nitrogen, sending these electrons onto this nitrogen here, resulting in the formation of R1N now having a negative charge. This will now become a single bond, which you can see here. This will now become a triple bond, which is shown here, right? So once again, this structure here is quite useful for the further type of reactions, okay? And now we will be paying our attention all towards this structure here, and we will see that how this structure will be leading to the formation of, first of all, this type of product and this type of product here, right? So let us first of all concentrate on the formation of this type of oxadiazole 2-one from this type of resonating structure, which we have got from where? From this mesoionic molecule, right? So this has just happened that from this mesoionic molecule we have got this type of resonating structure, which will be further used up for the formation of 2 different types of products. The first one is triazole, which you can see here, and the second one is the oxadiazole 2-one, right? So first of all, let us concentrate on the synthesis of this particular molecule. So here is the mechanism of the reaction here, in which you can see that this resonating structure will be acting as our 1,3 dipole, and because this whole reaction is occurring in the absence of an external dipolarophile, you can see here we are not adding anything here. We are not adding any other reactant or a dipolarophile molecule here. We are not adding anything, right? So in the absence of an external type of dipolarophile, what will happen is that while the formation of this type of resonating structure took place from the starting mesoionic molecule, you have seen that release of a molecule of CO2 took place, right? So now that CO2, which is C double bond oxygen with a partial positive charge on the carbon and a partial negative charge on the oxygen, this bond here can act as our internal dipolarophile, right? So whatever structure or the 1,3 dipole we have got here, it will now be reacting with the internal dipolarophile, which is what? Which is this CO2 molecule. You can see here it is this CO2 molecule here, right? So let me go back to our main slide in which the CO2 is acting as the internal dipolarophile. So once again I am just redrawing this 1,3 dipole in this way, and you can see here the carbon dioxide molecule is present in this way here with a partial positive charge on this carbon, such that it will now be interacting with the negative end of the dipole, and this oxygen atom, because it is having a partial negative charge, it will be interacting with the positive end of the dipole in this way, right? So resulting in the formation of a bond in between this carbon and this nitrogen in this way, which you can see here, right? It is this bond here, and moreover the second bond in between this oxygen and this carbon atom, which you can see here lying in this way, right? And moreover this triple bond here will now be it will now be transformed into this type of double bond, and this double bond here will now be transformed into a single bond, which you can see here in this structure, right? And now if you just compare this structure with this one here, it is exactly the same structure, right? So this is how, starting from this Sydnone mesoionic molecule in the absence of an external dipolarophile under photochemical type of reaction conditions, first of all we have seen that it results in the formation of this type of resonating intermediate, which reacts with the CO2 molecule as an internal dipolarophile undergoing a 1,3, let me write here 1,3 dipolar cycloaddition reaction, 1,3 dipolar cycloaddition reaction, the usual mechanism, resulting in the formation of our oxadiazole 2-one, I mean this second product molecule here, right? And now we will see that how from this structure we will get this triazole molecule on the next slide, right? So we want to see now that how the mechanism will go further and result in the formation of this type of triazole as the first product molecule. So here you can see the mechanism is something like this. So as usual, we will be starting from this resonating structure here, which you have seen that how we can get this from our starting mesoionic reactant Sydnone molecule. And now I have shown here the two molecules of the same intermediate, I mean this one. So an intermolecular type of reaction will take place here, and let's see how that will occur. First of all, this negative charge here, which you can see on this nitrogen, it will be shifting in this way, and then these pi electrons of this triple bond will be attacking on this carbon atom here, sending these electrons of the pi bond onto this nitrogen atom, right? So obviously this single bond will now become a double bond in this way. This triple bond, I mean this triple bond will now become a double bond in this way. The attack of this carbon atom on this one here will result in the formation of a new bond in between this and this. And of course, this triple bond here will now become a double bond, which is visible in this structure here, right? And we can say here that the only driving force here for this step was what? That the two nitrogen atoms here, they are having the positive charges, and these two are having the negative charges. I mean, there is a lot of charge separation here, but by this reaction, what will happen is that some of the charges has been dispersed. You can see here the negative charge has been dispersed here, and the positive charge has been dispersed on this nitrogen atom, right? And after that, what is going to happen is that this negative charge will again shift here in this way, sending these electrons between the carbon and the carbon single bond, and finally shifting these electrons onto this nitrogen atom, resulting in the formation of a double bond here instead of this single bond. Now a double bond will appear in this way. This will now become a single bond, which you can see here, a double bond now in between this carbon and this carbon atom, and moreover this will now become a single bond, and in doing so the rest of the charges here, they are also dispersed, right? So this is the driving force for this step here, right? And now please listen carefully that whatever I will be discussing here after this red line, it is from the research publication, the clippings of which I have attached in this video. It is from the tetrahedron letters, year 1970. The page number is 2275 and the volume is 26, right? Whatever mechanism I have shown here, I have taken from that research publication. What is happening is that I have just redrawn this whole structure here in this way, right? The pi electrons of this carbon-carbon double bond, they are shifting in between this carbon and nitrogen, sending these electrons onto this nitrogen atom here, right? This will now become a single bond like this. This will now become a double bond, something like this. And moreover, because now carbon here is forming 3 bonds, so better to show a positive charge here. And moreover, because of the shifting of these pi electrons onto this nitrogen atom, negative charge will appear here in this way, right? And after that, a very unusual type of step is happening here, that this nitrogen negative, it is attacking on this nitrogen atom which is already having these electrons, sending these electrons of the pi bond onto the adjacent nitrogen atom in this way, right? To be honest here, this step here is quite unusual, right? It is quite unusual. That is why I have mentioned here that I have taken it from a research publication. So let us go this way and let us see what will happen at the end here. So it will attack here on this nitrogen, shifting these electrons onto this nitrogen atom having already a lone pair, right? So what will happen is a new bond formation obviously will take place in between this nitrogen and this nitrogen atom in this way. This will now become a single bond from this double bond, and initially it was having one lone pair, and now we will be showing another lone pair which is coming from these pi electrons here, I mean of this double bond, right? So now if you look here and if you try to calculate the formal charge on this nitrogen atom, you will see that the formal charge is -1, because the formal charge is what? It is equal to the number of valence electrons in the free atom, means the free nitrogen atom, which are 5 in number, minus the number of valence electrons in the bonded atom. And in this case, the number of valence electrons are how many? 1, 2, 3, 4. 1 electron from this shared pair, I mean this shared pair, and 1 electron from this shared pair, right? So it is 1, 2, 3, 4, 5 and 6 here. So 5 minus 6 gives us -1, right? So that is why we are putting a negative charge here on this nitrogen atom. And now in the last, what is going to happen is that you can see here what is going to happen is that these electrons will be shifting here in between this carbon and the nitrogen single bond, giving a double bond with a positive charge here on this nitrogen atom, because it has given its electrons. Moreover, it is forming 4 bonds here, you can see very clearly in this diagram. And in the last, these electrons, I mean this electron pair here, will be moving towards nitrogen atom to disperse the positive charge here, resulting in the formation of a lone pair, and this will become neutral type of nitrogen. Moreover, what will happen to this part of the molecule? It is a nitrogen atom here, single bond R1. These 2 lone pairs as usual here, but it was also having a negative charge, right? And obviously when this bond electrons or these bonded electrons are going towards this nitrogen atom, what will happen to this nitrogen here? It will now be having a positive charge, right? So initially it was having a negative charge, and now because of the cleavage of this bond from here, it will now be having a positive charge. So positive and negative will cancel each other, it will simply neutralize each other. So ultimately will result in the generation of such type of intermediate here. These are known as the nitrene intermediates, right? So it will be good if we show here that in this photolysis reaction, in the absence of an external dipolarophile, we are getting what? A molecule of triazole plus the oxadiazole 2-on, the mechanism of which we have seen on the last slide, starting from this type of resonating structure. Moreover, what else we are getting here is a molecule of nitrene, that is R1N, with 2 lone pair of electrons, which are actually neutral type of species but are reactive in nature, right? So This is all about the photolysis of the Sydnone molecule in the absence of an external dipolarophile. So we have seen that it will result in the formation of this type of structure by this type of mechanism here, and then this structure, after reacting with CO2, it will result in the formation of this type of product molecule, and CO2 here was acting as our internal dipolarophile because it is released here within the reaction, right? And then we have also seen that how from this resonating structure we will end up with this type of triazole molecule with some very unusual type of mechanism. But I have a source for that mechanism, and it is this publication here, which once again let me read for you people. It is from the Tetrahedron Letters, a very respected type of journal in the world of chemistry, right? So here you can see that this is this structure here. I mean, the first structure here is what it is. It is this structure here. I mean, this structure here, right? And from this structure, let me write here number 1. So what we are getting here is 2. I mean, this is what, this is our triazole, which you can see here. It is this structure here. This is the triazole, or let me now write here, it is number 2, right? So you can even see the mechanism which is present on the second page of this journal or this research publication. It is giving a nitrogen negative in this way and a positive charge here on this carbon atom, which we have just discussed. And after that, this is simply attacking here on this nitrogen atom, giving these electrons onto this side, which you can see here, the formation of a bond in between this nitrogen and this nitrogen. And this one here is now having a negative charge, right? And finally, what will happen is that these electrons are shifting from here to here, giving a double bond. See, double bond N here. And of course, this will now be having a positive charge in this way. And to this one nitrogen atom and some R group here is attached, which is also having a negative charge with 2 lone pair of electrons. And finally, these electrons of the bond pair will be shifting towards nitrogen. Let me complete the rest of the structure for you people. This is carbon, some R group here, then 1 R group here, double bond, nitrogen, and single bond. This is also having 1 R group, right? So after the cleavage of this bond from here, what will happen is that it will result in the formation of, C, single bond R, single bond C, R here, double bond nitrogen, single bond nitrogen with this R group. This will now be a single bond nitrogen with a double bond in this way, right? And now because the electrons of this bond pair, they are going towards nitrogen, so I have to show it in this way, right? And what will happen to this part of the molecule which was having 2 electron pairs, now it will be, initially it was having negative charge, but now it will be having positive, and they will be dispersing, they will be neutralizing each other, resulting in the formation of a nitrene here, right? So you can see here, it is finally resulting in the formation of structure 2, which is actually this structure here, which is our triazole molecule, and this nitrene molecule here, which you can see here, it is this structure here, right? So this is all about the photochemical reactions of the Sydnone molecules. Thank you so much.